Hello everyone, in this video I will discuss diverse examples of synthetic applications of Peterson Olefination. But for a better understanding, you can watch the first part of Peterson Olefination where you will get the detailed mechanism and also some important features of this olefination. Without knowing that is all these features, it will be difficult to understand all these examples. You will get the video link in the description box and also it is right now appearing on the screen on the top right corner. Here we have the first example. And here you can see reagent, it is given Me3SiCH2MgCl. Ether is the solvent, and though the substrate it is looking very complex, but we have to focus on the actual reaction site. So it is the main important point for any name reaction is to recognize the reagent and where the exact reaction is happening. Okay, so in this molecule there is you can see so many chiral centers are there, but our focus will be on this reaction site. This is the carbonyl where this Me3SiCH2MgCl, this reagent will attack. So as here we have this organometallic compound, so there will be some carbanion type of character at this carbon and it will attack at this carbonyl carbon. Okay, so there will be formation of this beta hydroxysilane compound, and this beta hydroxysilane compound, in presence of this base, there will be removal of this OH group and Si-Me3 group, and in this position you will get a newly generated CC double bond. Okay, so in this way only this part, just compared with the initial substrate, this carbonyl compound it is converted to C double bond CH2. So this CH2, the source of this carbon is basically this carbon, that is between this Me3Si and MgCl. So in this way, though the molecule looks very complex, but ultimately if you focus on the actual reaction site and the reagent, you will find that this is a very simple reaction. Next example, here we have again Me3Si CH2MgBr. That means there will be some carbanion type of nature. And look at the substrate. There is C double bond O, that means carbonyl, where the actual reaction will take place. Rest of the compound there will be no change. And here we have OSI-Me2TBU, but that has nothing to do with the reaction. It is simply a protection of this OH group that is in the form of OSI-Me2TBU. Okay, but mainly reaction that will take place here, and there will be fast formation of this beta hydroxysilane, and after that there will be in presence of acid, because this reaction can happen in presence of acidic medium as well as basic medium, and that all these are discussed in the first part. You will get the details, and here removal of these two groups, ultimately there will be formation of a new CC bond at this position. So the source of this CH2 in this newly generated CC bond, the source is basically this CH2 group. Okay, example 3. So this is very simple. As you can see, already the beta hydroxysilane compound that is already present, that is the starting matter itself is there, we don't have to make it. And in presence of acidic medium, again there will be formation of OH2 plus. You can get the details in the mechanism, I am not showing it here. And finally, after removal of these two group, we will get a newly generated CC double bond in this position. So example 1, 2 and 3, they are taken from books, and I will mention it in the description box. Next example, it is taken from this reference, as you can see, and here ArCOR, that means we have a carbonyl compound. First we have to prepare this beta hydroxysilane, and then we will see the actual elimination step. Here we have this compound TMSCH2MgCl, trimethylcyl CH2MgCl. So there will be carbanion type of nature in this carbon, and this carbanion that will attack here, and we are getting this intermediate beta hydroxysilane compound. Now in presence of this molecule, which is bis-trifluamide acid, that is bis-trifluamidic acid, okay, HNTF2, and you can see very low catalyst loading. So that is the beauty of this reaction. So in presence of this type of reagent, this acid is milder version of trifluic acid. Finally, this OH and TMS group is removed, and we are getting terminal alkene. Okay, so this CH2 that is coming from this CH2 of TMS CH2MgCl. And here R groups, as you can see, it may be hydrogen PHET, and air is benzene ring on any heteroaryl group, and even this R group can be this type of group also. If you look see the paper in detail, so there is triple bond and then trimethylsilyl group, That means this R group, if you write this group, so basically by this method you can produce a enine type of molecule, because there is triple bond and there is double bond. So that is very interesting feature of this reaction. In presence of this Bronsted acid HNTF2 beach triflumidic acid, we are getting finally these varied type of products, where one of the product may be even enine. Next example, new Peterson reagent for the synthesis of Z alpha beta unsaturated sulfone. So here you can see, normally we have seen if you look at the previous, consider the previous example, it is mostly Si-Me3 group or any Si alkyl group, but here look at this group, it is very interesting, very different type of group that is attached to Si, and there is also SO2 pH group, and that is electron withdrawing group. So in presence of this base, as you can see, the base is also given, and this type of base structure details you can find in Julia olefination reaction. The link for Julia olefination I will also mention in the description box. So there is a group SO2pH, and there is also a group Si, that is substituted Si. So in presence of base, there may be some confusion of whether it is Julia or Peterson, but actually here Peterson elimination is taking place. Okay, so there will be negative charge generation at this position, and in presence of CpMe or DMe. So these are the solvents: cyclopentyl methyl ether or 1,2-dimethoxyethane, short form CpMe DMe, and this will attack this carbon aldehyde RCHO, where R may be these type of groups: alkyl, vinyl, CpMe solvent for alkyl vinyl, DMe solvent for aryl group, and we are getting Z alpha beta unsaturated sulfone, because this is Z and this is alpha beta unsaturation with respect to this SO2pH. So this type of special reagent that is only producing this type of Z compounds, that is Z alkene. Okay, so Z alkene or E alkene, all these detailed discussion you will find in the part 1. So if you are interested, please watch the part 1, because here I am focusing only on the examples. Next example, Peterson alienation. Alienation means if you look at the final product, there is alene, right? So that is why it is alienation. So look at the first arrow. Here in presence of base, there will be negative charge over OH, and that will ultimately interact with this Si. So just rotate this bond, you will understand. There will be this type of 4-member ring. So this is the intermediate and this is a counterant, and finally these two groups will be removed, and there will be CC bond generation at this position. So this is our alene, right? So this is also very interesting because we are getting that is the newly generated CC bond. It is just generated just adjacent to the originally present CC double bond in the substrate. So that is why we are getting alene type of compound. As a Peterson 2-axis 1,3-diene. Now until now we have seen carbonyl compounds. It may be aldehyde, it may be ketone, but now you can see phenyl substituted imine, right? And also this Si-Me3 containing compound, where that is another reaction partner for Peterson olefination. Here also we are seeing two Si-Me3 group, but actually we have to focus on this CH2, where the actual reaction will take place. So this CH2 and this carbon, the actual connection will be taking place between these two. Okay, so if you look at the product, this side we are getting from this imine, that is ARC, and the other part that we are getting from the another reaction partner, because this Si-Me3 group that will be ultimately removed once that is here the intermediate not beta hydroxy, it will be different. Intermediate is not shown, but ultimately this left hand side part that is coming from the first reaction partner, right hand side part that is coming from the second reaction partner, and the squared I have just highlighted this Si-Me3 group, ultimately it will be removed. But whatever it is, the final compound is 1,3-diene. This is 1,3-diene. So from this reaction we can generate 1,3-diene. So this double bond, it was already present in the substrate in one of the reaction partner, and this is our newly generated CC double bond. Next reaction that is also taken from the same paper. So see, this substrate, it is same, it is N phenyl substituted imine, and the other reaction partner. Now we have Me3Si CH2PH. That means if you look at the product, this side will come from the first reaction partner, and the right hand side part that will come from C, that is the second reaction partner, and this Si-Me3 group that will be. So in this way we can we can get some excess Stilbene derivatives, and this reaction they are calling, that is as the name is given in the paper, they are calling it Aja-Peterson to access 1,3-diene or 1,3-Stilbenes. And all these references I have mentioned it, and also you will find it in the description box, because if you want to copy paste this DOI, that you can do from the description box. So I hope this video will be helpful to you, and thank you for stopping by.